Welcome to session 10 of small signal operation and models. In this session we are going to study about small signal equivalent circuit models and some of the expressions for the transconductance. Now in the previous session I have given some introduction about small signal equivalent models and what are the various components it includes. So now let us see how to draw the small signal equivalent model. Now here particularly this equivalent representation is useful whenever MOSFET amplifiers are analyzed for different factors like voltage gain. Okay. So in the analysis the device MOSFET is replaced by its equivalent circuit, and here you can see figure A shows the small signal equivalent circuit for the MOSFET. Now in order to draw this small signal equivalent circuit, so ideal constant DC voltage sources are replaced by short circuit, and also the constant DC current sources are replaced by open circuit. And now the resulting signal, after doing these many settings, the resulting signal is used to perform the signal analysis. Okay. Now in figure A, the major demerit is it assumes that in the saturation region the drain current is independent of the drain to source voltage, but practically it is not so. So even in the saturation region also, so there is a dependence between ID and the VDS. Okay, so therefore this small signal equivalent circuit, okay, so it is considered without considering the resistance effect in the saturation region, and it considers that ID is totally independent of the VDS region. So this small signal model it includes VGS, that is the small signal between gate and source terminal, as well as there is GM into VGS, that is this is the current source, so between drain and the source terminal. So that's why we call this device as a voltage controlled current source. So changes in the VGC are going to control changes in GM into VGS. See, now we will write some more. We will try to include the saturation region conditions also. So for example, here you can see a graphical representation which shows the curves, that is the relationship between ID and VDS in the saturation regions. Okay, so in the saturation region we can see that the curves have the slope 1 by R0. So it means that there is a finite resistance associated in the saturation region. So therefore that value of resistance R0 has to be included in the small signal equivalent circuit. So where R0 is given by VA by ID, so where VA represents 1 by lambda, it is related with the channel length modulation phenomena in MOS devices. Okay, so that R0 is modeled using VA and the drain current ID values. So the R0 in the saturation region, it is typically in the range of 10 kilo ohms to 1000 kilo ohms, but this R0 has to be included in the small signal equivalent circuit. So after including R0, okay, so the equivalent circuit becomes as shown in figure B. Okay, so here R0 we call it as a output resistance. So just observe the input side, again the same VGS we have, there is a GM into VGS, but only thing is now that effect of R0 has come between drain and the source terminal. So we can consider this as a complete small signal model for the MOSFET. So next another important aspect related to these MOSFETs or this small signal equivalent circuit is, by including the R0, what is its effect on the overall gain of the circuit. Okay, so therefore here a MOS amplifier circuit diagram is shown. So with respect to this only, so we are going to discuss this and we are going to write what is a new gain equation. Okay, so we considering this MOS amplifier circuit, we have redrawn the complete small signal model by including the resistance R0. Now when this model is replaced, when the MOSFET is replaced by this model, the drain resistor RD in the circuit is going to come in parallel with the R0. Okay, so that is our equivalent circuit for this MOS amplifier circuit. It looks like this. So the RD resistance is going to appear here, and this is the drain terminal. Okay, so this is a small signal I am writing for this amplifier circuit. So where RD has to be included and it will come in parallel with the R0. Okay, so therefore now whenever we are writing the gain equation, so this will be equal to that is, first I am writing the output equation, that is instantaneous VD. So VD will be equal to current into resistance. So here current is nothing but GM into VGS. But now when it comes to resistance, so now we have to write that this R0 comes in parallel with the RD. R0 coming in parallel with the RD. Okay, so therefore for this particular arrangement, the gain equation AV, is simply VD divided by VGS. So this will be equal to minus GM into RD parallel to R0, because so this VGS, numerator denominator VGS are going to cancel. So therefore AV is equal to minus GM into RD parallel to R0. Okay, so this is the new value or the new expression for the gain after including the output resistance R0 in the circuit. Okay, so therefore the effect of this finite output resistance R0 is reduction in the magnitude of the voltage gain. Okay, so this is going to, R0 is going to reduce the magnitude of the voltage gain. So this is all regarding the small signal model for the MOSFET. So next we'll move on to the transconductance GM for the MOSFETs. Now here we are going to write what are the different expressions available for the transconductance factor GM. Okay. So we will start with the very first MOSFET transconductance equation. That is, we know that the GM is given by, GM is equal to ID by VGS. Let us take this as equation 1. But our drain current ID is nothing but Kn dash W by L VGS minus VT into VGS. Okay, so we call this as equation 2. So I hope you remember this equation 2, that is ID equation. So this is nothing but at the drain terminal, it is the current component at the drain terminal. Okay, so I think in that derivation we had 3 parts. One is the DC drain current, second one is the signal component, and third one is a VGS square term. Okay, so in that we are considering the current because of this small signal VGS. Okay, so and also it should be clear for you that this VGS represents the DC bias and this small VGS represents the signal component. So therefore the ID is given as in equation 2. So now by substituting this equation 2 in 1, so we can write an expression for GM. So substitute here Kn dash W by L VGS minus VT into small VGS divided by small VGS. Okay, so here the VGS term cancels, and now we have an expression for GM which has only this Kn dash W by L, which is nothing but the process constant, and you should be knowing that Kn dash is nothing but mu n into C oxide. Mu n into C oxide is the Kn dash value. So but anyway we will keep it as a constant, and the remaining term is VGS minus VT. VGS minus VT. Let us call this as one equation 3. But we know that this difference VGS minus VT can be written as the gate to source overdrive voltage VOV. Okay, so therefore now we can write GM as Kn dash W by L into V overdrive voltage. Okay, so this is one important relation for the GM. Okay, so we will take it as a equation 4. Then it is also observed that the GM is proportional to Kn dash W by L ratio of the transistor, and also it is proportional to the gate to source overdrive voltage VOV. Okay. Now yet another representation for GM can be obtained by using the drain current equation. What is the drain current equation we have is, we know that ID is equal to half Kn dash W by L into VGS minus VT whole square. Okay, so now in this we'll modify the equation little bit by rearranging the terms. Okay, so this 2 into ID divided by Kn dash W by L, so it is transferred on the denominator side, and here if I am writing only VGS minus VT, so here I have to take the square root. Okay, so now I have got one more representation for this VGS minus VT, which is nothing but gate overdrive voltage. Okay, so let us take this as one intermediate result, equation 5. So now using this equation, it is possible to again rewrite the GM as Kn dash W by L into 2ID by root Kn dash W by L. Okay, so GM is equal to 2 Kn dash into W by L ratio into ID. Okay, so this is another representation for GM. So what we have done here is simply in equation 4 we have replaced VOV, because this term is nothing but VOV. Okay, we have replaced V overdrive voltage by root of 2ID by Kn dash W by L. So it is possible to get an alternate expression like this. So therefore this represents one more important expression for GM. Okay, so we can take it as equation 5. So now from this equation we can see that the GM is directly proportional to square root of the DC bias current, that is ID, as well as it is directly proportional to this W by L ratio of the transistor also. Okay, so fifth one is the another representation for GM. So still one more expression for GM can be obtained by substituting for this constant Kn dash W by L. For that we will make use of again one more drain equation only. So we know that ID is given by half Kn dash W by L into VOV square. Okay, so what is this? ID, drain current equation in the saturation region, which is given by 1 by 2 Kn dash W by L VOV square. So now in this we will substitute for this term, that is what is Kn dash W by L. So therefore that equation gives Kn dash W by L is equal to 2 ID by VOV whole square. That is, I am retaining only Kn dash W by L on one side, so remaining all terms are transferred on the other side. Okay, so therefore I will get equivalent for Kn dash W by L value. So now we have from the previous discussion that GM is given by Kn dash W by L VOV. Okay, so now we will substitute what is this Kn dash W by L from the above equation. Okay, so therefore substituting from the above representation, Gm is nothing but 2 ID by overdrive voltage into VOV. Okay, so one term gets cancelled, so this gives us 2 ID by VOV. Okay, so therefore we have the Gm is equal to 2 ID by VOV, but VOV is nothing but again equal to VGS minus VT. Okay, so this is another expression for the transconductance Gm. So we can write equation 6. This is equation 6. Okay, so therefore we have as a summary the transconductance Gm is given by, first one, Gm is equal to Kn dash W by L VOV, gate overdrive voltage at which the MOS amplifier is operating. And next we have one more expression for transconductance Gm is equal to 2 Kn dash W by L into root ID. Then we have one more, Gm is equal to 2 ID by VOV, or this is equal to 2 ID by VGS minus VT. Okay, so in the problems, if any one of the factors, depending on the given factors in the problem, you can make use of any one of the equations to find out the transconductance. So therefore with this we have come to the end of all the topics in the module 1. So this is the reference. So all the circuit diagrams, graphical representations, as well as the problems discussed, they are all taken from the Microelectronic Circuits Theory and Applications by author Adele Cedra and Kenneth Smith. Thank you.